Oh, I'm so sorry. So thank you for everyone. My name is Tatsuhiro Shimizu, and today I'm going to talking about effective O4C evaluation and learning in contextual combinatorial bandits. So in recommender systems, we are sometimes interested in the recommendation of the combination of items. For example, the combinations of the fashion items, or the combinations of the pieces of furniture, or the combination of the medical pills. So under such situations, how can we evaluate or learn a policy effectively? So at the end of this presentation, we are going to answer such questions. So before proposing a new method, we are going to firstly formulate a problem by contextual combinatorial bandits, CCB. In CCB, we are interested in three variables. The first is the context S, which is a user information in recommender system. Then we define the subset action, which is a combination of items in recommender systems, and the subset of the action space, where the action space is the set of the unique actions in recommender system. Then lastly, we define the reward R, which might be the click rate or conversion rate in recommender system. Then in terms of the data generating process, we firstly observe context from an unknown distribution. Then given context, we observe subset action from a stochastic policy, which is a known distribution because we can implement a stochastic policy. Then given context and subset action, we can observe reward from an unknown conditional distribution given context in a subset action S. Then following these three distributions, we can create log bandit data, which is the NIID sample from these three distributions. And we call a policy that is used to correct the log bandit data a behavior or logging policy. Then for those of you who know about the O4C evaluation, CCB is a different problem from ranking and straight contextual bandits in terms of the 2 points. The first point is that the number of actions. In CCB, we consider the combination of items. So the number of actions grows exponentially fast compared to a ranking and straight. And secondly, in CCB, we can only observe a single reward corresponding to the combination of the items, which is not the case for the ranking settings. So having that in mind, we are going to define the problem of O4C evaluation, OPE. In OPE, we aim to evaluate the value of an evaluation policy, where the value function is defined as the expected reward, and we also define the conditional expected reward function, QXS. And we also define the measure to compare the estimators, and we use a mean squared error, MSE, which can be decomposed into the square bias and variance. So it is important to reduce both bias and variance to create an accurate estimator. Now we are going to introduce two existing methods and their limitations, particularly adapted to the contextual combinatorial bandits settings. The first estimator is called direction method, DM, and DM replaces the estimated expected reward, Q hat, for the true Q. The great thing about DM is the low variance. However, when applied to contextual combinatorial bandit settings, it incurs significant bias because it is extremely difficult to create an accurate estimator for Q hat. In contrast to the model-based approach like DM, inverse propensity scoring, IPS, is a model-free approach that does not rely on the model. And it weights the observed reward by importance weight, which is the ratio between the propensity score of an evaluation policy and the logging policy. The great thing about IPS is that it is unbiased under the common support. However, when applied to CCB, when we wanted to ensure this common support assumption, it incurs significant variance because of the variance from the importance weight, defined on a huge set of the combination of actions. So to overcome these limitations, we are going to propose a new method. And to do so, we are going to introduce two key ideas to construct a new estimator. The first one is the factorized action space. And we represent the set of the combination of items by the Cartesian product of a specific set, ML, where ML is the set of empty set and the elf element in the corresponding element in the action space. And the great thing about the introduction of this factorized action space is that we can focus on the specific key actions rather than treating the combinations as a whole. For example, we can consider these 6 recommendation items, and we can define a factorized action space, which is a set of the combinations items. And we can also define the element in such kind of factorized action space. For example, when we wanted to consider the set of, when we wanted to consider the combination of the tops, bottoms, and watch, then we can use M1 to represent it. The second key idea is decomposition of the expected reward function, where we particularly decompose into main effect and residual effect, where the main effect captures the effect of the main actions, phi m, in the combination of the items, whereas for the residual effect, capture the other effects that was not captured by the main effect. The great thing about this decomposition is that we can treat each effect differently to overcome the vicious cycle of bias variance trade-off of the existing methods. Then coupled with these key ideas, we propose a new method, ortholycy estimator for combinatorial bandits, OPCB, where the OPCB estimator consists of 2 terms, where the first terms deal with the main effect by using the importance way, defining on the set of the main actions, which is much more compact compared to the set of the combination of items. And the second term deals with the residual effect using the regression model F hat. The great thing about this estimator is that we can reduce the variance by importance way on the main actions phi m. Whereas, and secondly, we can also deal with the residual effect via regression model F hat. We also derive theoretical properties of this estimator, and we derive that OPCB is unbiased under conditional pairwise correctness, CPC, which is a weaker assumption than DM. And CPC requires a regression model F hat to be pairwise correct for any 2 combinations of the items if they share the same main actions, which is, again, weaker than the DM assumption. In contrast to the bias, we have also derived the variance of OPCB estimator, and the variance of OPCB estimator does not rely on the importance way on the set of the combinations items, but this weight on the main actions, which is much more compact than the set of the combination of the actions. So we can reduce the variance of the IPS estimator. Now we are remain to optimize the set of main actions, and we optimize it by using the approximated MSE, where the approximate MSE is the square estimate of the bias of OPCB plus sample variance of OPCB. We have also conducted an empirical evaluation of this estimator, and firstly, we are going to talk about a synthetic data experiment where we particularly validate the number of actions. When the number of unique actions increases, the baseline estimators suffer from either bias or variance, as we talk about in the theoretical analysis sections. However, our estimator can evaluate the value of an evaluation policy the most accurately thanks to the reduction of the variance. We have also conducted a real-world data experiment on the quiet recommendation data on a video sharing app, and we have also seen that our estimator can evaluate the policy most accurately for the real-world data, which ensures the real-world applicability of our estimator. And we also have seen that the OPCB is robust to the noisy bias estimation, which ensures the data-driven optimization of the main actions. So that's it for my presentation. These are the references, and thank you for listening.
Thank you, Tatsuhiro. Are there any questions from the audience in the room? No? We have a question on Slido. How do you decide which actions are main actions and which are residual?
Okay, let me go back to the slide on. So just to make sure, the question was about how
do you decide which actions are main actions and which are residual?
Okay, so I think it's about this optimization procedure. So for each combination of the items, we can define the main actions, and that's going to be the function shown in this slide, phi, and we can define the several functions, which is like a capital phi, and among these functions, we can find the best function that can distinguish like a main effects and residual effect, which minimize the MSE of the proposed estimator. So that's how I can distinguish these effects. Is that correct?
So that was it.
Yeah, that's that.
Okay, any more questions? If not, let's thank the speaker again. So